We can also do an acid catalyzed dehydration, and we've seen this reaction actually. This was involving water and acid plus a high amount of heat. That'll do a dehydration. So we're going to remove water, and then we get a double bond in its place, plus H2O. The general reaction is that we form an alkene from an alcohol through the loss of water, which is called a dehydration reaction. And we've seen a little bit of this forming alkenes a few chapters ago. We have the alcohol and then the hydrogens that are next door. And you can get two products. One where our alkene is here, if that one is removed, or this one. This is the major because that's a more substituted alkene. This is the minor because it's disubstituted versus the trisubstituted. We can also oxidize alcohols. If we have a primary alcohol and we use an oxidizing reagent, this will first form the aldehyde. And this reaction will continue because there's still a hydrogen there on that aldehyde. And we get the carboxylic acid. So oxidation is loss of hydrogen and or gain of CO bonds. So here we've lost this hydrogen to form the aldehyde. There's still a hydrogen here that gets lost and replaced with the CO bond to give us the carboxylic acid. If we have a secondary alcohol, that hydrogen gets lost. We lose the hydrogen and leave behind a double bond to form the ketone. And with the tertiary alcohol, there are no hydrogens here, so there's no reaction. Another reagent that we can use that is milder is the Des-Martin pyridinane. You don't need to know the structure of that. Those OAC groups are acetate groups, which are shown here. We're just going to use DMP as the acronym for this. So this is the abbreviation. The Des-Martin pyridinane is a milder reagent that will stop primary alcohol oxidation at the aldehyde. So if we have one hydrogen here, that will get removed, and in this case we're doing the reaction with geraniol, which is used in perfumes, comes from roses. So here is our aldehyde that's formed, and if we had used one of the other oxidizing reagents, that would go to the carboxylic acid, but this Des-Martin pyridinane will stop at the aldehyde to give us geraniol. So we can use DMP for alcohols to give us aldehydes. If we want to oxidize an alcohol to the carboxylic acid, we can use sodium dichromate. This is also known as the Jones reagent. So that's going to remove this to give us the aldehyde, and then we're going to replace that last hydrogen with the OH. So here is our oxygen, and we leave behind the carboxylic acid. So this is decanoic acid. And then we also can do this with 4-tert-butyl-cyclopentanol, and we only have one hydrogen here. We just have the one hydrogen here, so this is a secondary alcohol. This will be oxidized to the ketone. We're not going to do anything else with any other carbons or groups, and we get a ketone. So this reagent is used in breathalyzer tests, so hopefully none of you have had to encounter one of these, but a subject blows into the mouthpiece, and if any alcohol that's in the person's breath will react with the Jones reagent that is sitting in the breathalyzer, and that reacts with the light source to show us with the light source via IR. So if you remember doing IR to check functional groups, that's what's happening inside of this breathalyzer. So the IR is going to find the alcohol groups, and it gives off a certain amount of light that passes through, and that will translate into the percent blood alcohol. So we've got some practice problems here. We have a secondary alcohol. We have one hydrogen here. That's going to get removed to leave us a double bond. So we'll get a ketone as the product. If we use Des-Martin pyridinane, this is the reagent that will oxidize our primary alcohol to a carbonyl, and it will stop at the aldehyde. If I do that same reaction using sodium dichromate instead, that one is not going to stop at the aldehyde. That will keep on going. We're going to get the carboxylic acid. And if I react tertiary alcohols with sodium dichromate, there are no hydrogens here to get oxidized, so this is a no reaction. Sometimes you might have a compound that has more than one functional group. If you do reactions, you have to be careful that your reactions aren't going to interfere with the other group. For example, if I tried to form a Grignard with a compound that had a bromo group and also an alcohol, it's not going to form. In order to do these reactions, we have to use what's called a protecting group. In this case, we can use something like trimethylsilyl chloride. This is abbreviated TMS chloride, in the presence of a base. So this is a mild base. And what that's going to do is it's going to protect the alcohol and kind of put like a cap on it so that the reagents don't see the alcohol. So instead of having a hydrogen on this alcohol, we're going to add this trimethylsilane. So because we put this TMS group on that oxygen, any other reagents that normally would react with an alcohol can't see it or feel it. So the alcohol is in disguise. So when you're doing a reaction with protecting groups, you first want to protect the alcohol, which we've already done. There's this TMS group on there. Then you make your Grignard if that's what you want to do. So our alcohol doesn't react with the Grignard. And now we have our Grignard reagent. Then we do the reaction. So I'm going to add this Grignard reagent to this formaldehyde. And the Grignard reagent is not going to react with our silyl group. So this is what we're adding. We added one carbon here. Okay, so the starred carbon is this one right here. I need to draw this extra methyl group that was right there. And then now we remove the protecting group using acid and water. And that becomes an alcohol again. When looking at reactions of sulfur, there's not that many that we're going to deal with in this class, but one of them is a nucleophilic substitution, which we have seen before with SN2 reactions, where the SH- is acting as our nucleophile. Here's our electrophile, so we'll get a nucleophilic hug here, and Br is our leaving group that leaves. So we'll replace that Br with the sulfur. So that reaction we've already seen. Another one that we can do is to form a disulfide. We add iodine to this reaction. That's going to replace each of these sulfurs, and then sulfur can act as a nucleophile and attack itself. We'll end up with a disulfide. So we form a new bond here to another unit of the sulfur. So this is a disulfide. And then we end up with two HI that's left over. So disulfide bonds occur in curly hair. So if you have naturally curly hair, there's several of the cysteine residues, which are amino acids that contain sulfur or thiols, and these get together, combine and form these disulfide bonds, which lead to curly hair. There's also a glutathione GSH, which is in biological processes, and these remove harmful oxidants. If you are reducing or chemically straightening your hair, you can use reagents to remove the disulfide bonds in your curly hair. But if you add zinc in acid to the disulfide, that will reverse the reaction to the thiol. Next, we're going to look at ethers and sulfides. An ether is a compound that has an oxygen with carbons on either side of the oxygen. Simple ethers are named by identifying the two groups that are on either side of the oxygen. So if I'm going to use simple naming for this ether here, I just list them alphabetically. I have an isopropyl group and a methyl. So this will be isopropyl methyl ether. And here I have a methyl and a phenyl. I list them alphabetically. This is methyl phenyl ether. If there are other functional groups present, the ether part is considered to be an alkoxy substituent. So on this benzene, instead of listing it as a dimethyl something phenyl, because it's a complicated structure, we're going to treat these as a methyl on an oxygen. So this will be methoxy. We have two of those, and they're para to each other, so this is para-dimethoxybenzene. And then here we have a tert-butyl group on the other side of the oxygen that has less carbons. This will be the parent, which is cyclohexene. So this is a tert-butoxy, and this is at carbon 1 for cyclohexene, and so our tert-butoxy is at 4. So this is tert-butoxy cyclohexene. Sulfides are like ethers, but instead of the oxygen, we have a sulfur. So when we're naming these, we just replace sulfide for ether. So this is dimethyl sulfide. And here is methyl phenyl sulfide. And here we have a more complicated one. So this will be a methyl thio on the cyclohexene. So this will be 3-methyl thiocyclohexene. Next, we'll look at some practice problems. In this one, the two groups are the same. So this could be diisopropyl ether. You can use simple naming for that one. This one is a little bit more complicated, so we're going to treat this as a substituent. So this is an ethoxy because there's 2 carbons here. We have the bromo. The lowest numbering to give us the lowest alkene would be at 1 bromo. So this is 1 bromo, 3-ethoxy cyclopentene. And then this is a more complicated one as well. I'm going to treat this as a substituent, so this will be an ethyl thio. Methyls at 2. The ethyl thio is going to get listed first alphabetically, so this will be 1 ethyl thio, 2,2-dimethylpropane. One of the ways that we can make ethers is to use something called the Williamson ether synthesis. And this involves first adding a base such as sodium hydride. This hydride is strong enough to remove this proton. And when we do that, we're going to form the alkoxide. So that's going to act as our strong nucleophile, and that's in the presence of sodium ion now. And this is our nucleophile that can then attack this electrophile. Kick off the iodine leaving group. And we add 1, 2 carbons. This is 1, 2. So this reaction of metal alkoxides works best when you have a primary alkyl halide. And that's because we're doing an SN2 reaction, which involves that backside attack where we don't want steric hindrance to slow down our reaction. And then we can make these alkoxides using the strong base like sodium hydride. Okay, so if I want to make this compound, this is our target molecule. TM is target molecule. There's 2 ways that we can make this molecule, and you can start with the different alcohols. So in the first situation, if I start with tertiary butanol, where this methyl group is getting added, I start with sodium hydride to make the alkoxide. I have my O, which becomes O-, and then I tack on the CH3 group. Here I'm dealing with the primary alkyl halide, so this is going to be a fast reaction. In this scenario here, I start with methanol. I have sodium hydride, and then this reaction is not going to work because I'm trying to do an SN2 attack on a tertiary carbon. One reaction we can do with ethers is to cleave them. So after we form an ether, we can revert back to an alcohol that was used to form it, and we add acid in the process. And so if we add acid and water, that can cleave the ether side. So I get an OH, and the other side, the CH2CH3 side, is going to form a bond to the Br that was used in the HBr. So H will go to the one side, and Br will go to the other side. And in this process, we'll get an OH. The H goes to the side that has more substituents, and then this will get the Br. The hydrogen is going to go on the oxygen on the side where our carbon has more substituents. So it would be this versus this one. This is our major product. So we have secondary alcohol versus the primary. An ether that we've already seen is an epoxide. These behave differently than regular open chain ethers because they're cyclic and they're much more reactive. Having that 3-membered ring increases the reactivity because we have angle strain. So we have nice juicy electrophiles right here with an oxygen leaving group built in. When we react an epoxide with H3O plus or acid and water, we get a diol that is anti. If we react it with HX, we get a halohydrin that is also trans. And that's because we're getting a backside attack of the nucleophile. So in these ring opening reactions, if we have a nucleophile, this is considered under negative conditions or basic conditions. So we have that negative nucleophile. It's going to do an SN2 attack at the less hindered carbon. So the one that has the least obstacles. We have many different nucleophiles possible here. If you remember what nucleophiles we use for SN2, those same nucleophiles apply here. So my nucleophile is going to go to the path of least resistance, which is right here. And that's going to form enough bonds. So this one's going to break open. Here's my bond to the nucleophile that we just reacted it with. This becomes O minus. And usually we have another step here with water, which can then protonate our alcohol. So other nucleophiles that you could use, X minus, any Grignards, CN minus, SH minus or SR, N minus. The thing that you see that's common here is that these nucleophiles are all negatively charged. I have a primary alcohol. This is an oxidizing reagent. Primary with an oxidizing, that's the sodium dichromate, is going to go to the carboxylic acid. And if it's easier to see what's going on, you can just draw it this way. Okay, and then secondary alcohol, same oxidizing agent. I have my hydrogen here, so I should get a ketone. I have sodium hydride, which will take off this hydrogen. That will form the alkoxide, which can react with this alkyl halide. So I form the ether here, and I add 1, 2 carbons. So 1, 2. All right, this one is a Grignard. That MGBR tells us it's a Grignard. So my nucleophile is the carbon that's next to the Mg. That's going to the path of least resistance, which is this one here with no obstacles. That will open up. So here's that oxygen that opened up, that methyl that was there. I add CH2CH3, and then that will become protonated with that acid. This should be plus up here, not down here. And then with MCPBA, that's going to form the epoxide. We get the addition of acid and water. So when we have this MCPBA, that's going to form the epoxide. If you want to put the intermediate here, you can. And the acid and water will open up to give us a trans diol. So other reactions that we can do with sulfides include some oxidations with hydrogen peroxide. So this is an oxidation reaction. When we did oxidations before with alcohols, we gained CO bonds, but with sulfur, we're going to gain SO bonds. So this becomes a sulfoxide, where we gain 2 bonds to oxygen. We add another peroxy acid here. This is a peroxy acid. So we add a peroxy acid, and then we can form the sulfone, which is further oxidized. Instead of having just 1 double bond oxygen to sulfur, we're going to have 2. This is a sulfone. And then a couple more reactions here. This is a sulfur ion, which can do an SN2. So we add the 2 carbons, and the sulfur can attack here, SN2. So we get a methyl addition here. So this is positive, and we get the I minus counter ion. This reaction can be called the methylation because we're adding a methyl group. And this actually occurs a lot in biological systems. Sometimes it can trigger your body to form different kinds of cells based on how methylation reactions occur.